Hey, welcome back. That's right. We are back. Smiley. So now that we have proven the squeeze theorem, let's use it. Use it. Okay, so the first thing we're going to prove is that the limit as x approaches 0 of sine of x over x is 1. That one right there. It's special limit number 1, and once we prove it, we can use it. Once you prove it, you can use it. Well, the cosine of x is less than or equal to the sine of x over x is less than or equal to 1. Okay, so this is clear from the graph or a table of values, either one you want to use. So here's my little graphs. The cosine of x is clearly below the sine of x over x. It's clearly below 1. Okay, you can look in the textbook when they give you these special limits if you'd like more information on how we got that inequality there. But once we establish this inequality, we can set up the squeeze theorem. So we look at the limit of our two functions that we're squeezing sine of x over x in between. The limit of cosine of x as x approaches 0 is 1. That's our transcendental limit, so we just plug in 0. Cosine of 0 is just 1, it's fine. And the limit of 1 as x approaches 0 is 1. It's a basic limit. It's actually theorem 2.1. Sorry, that was a problem. We use the squeeze theorem to conclude, therefore, that our limit of sine of x over x is also 1. Well, that was easy. It was really that easy. Okay, so 2, we're going to show that the limit as x approaches 0 of 1 minus cosine of x over x is 0. We'll use theorem 2.7, and we'll use a function that agrees that all but x equals 0. So the limit as x approaches 0 of 1 minus cosine x over x, let me multiply it by something over itself that just equals 1. Okay, so then what we get is 1 minus cosine squared x on the top. But notice, sine squared x plus cosine squared x is equal to 1 over here on the right. That's the Pythagorean theorem identity. So sine squared x is just 1 minus cosine squared x, and that's why I put that in there. So now we've got the limit. It's just sine squared x over x times 1 plus cosine x. So then you break this apart. It's really sine x over x, and then sine x over 1 plus cosine x. Okay? Now you've got your sine x over x. You break up the limit. That was theorem 2.2 product property. We know this one from above. So sine x, the limit of x approaches 0 of sine x over x. And sorry, my hand is a little bit, my writing is a little bit ahead of my speech here. Pardon that. So the limit of sine x over x is equal to 1. So we pull that out. And then we just break apart this limit as shown here. So we use the quotient property, and then we see up top that we've got the limit as x approaches 0 of just sine x, and that's just 0. Why? Because the transcendental limit, we can actually just substitute in, use direct substitution, so we get 0 up there. Down below, we now have the limit of 1, and then we've got the limit of cosine x. Well, the limit of 1 is just one of our basic limits, that's theorem 2.1. And the limit of cosine of x is again a transcendental limit, and so we can do direct substitution. So we have at the bottom there 1 times 0 over 1 plus 1. Look, that's just 0, which is exactly what was desired. So we transformed the function by multiplying by something over itself into a different function that we could then evaluate. So we use theorem 2.7. All right, secret word is going to be baby pie. I don't know what baby pie is, but I figured it was funnier than baby cakes, so it's baby pie. That's a secret word. All right, so that bottom one was the application of 2.7. This top one is the application of 2.8. Congratulations.